It's easy when you first learn a formula or a topic to get kind of lulled into a state of comfort with the equation and to start to think that something like our F equals ma, that I don't need to be too exact with it. It's just three variables. How hard can it be? I really want to show you in these three examples how creating a free body diagram and using that diagram to build the equation can really give you a great strategy that can be used for any type of problem, no matter how complex it gets. Especially if you hope to do something further with physics, if you just sort of learn how to do the easy questions and or sort of memorize how to solve certain problems, it's going to fall apart later. So get yourself into some good habits here. Take a look at these examples. Feel free to stop the video at this point if you'd like to copy down the problem and read through it more carefully before the solution is shown. So this box is moving with an acceleration as it's going across a horizontal surface. Let's begin by drawing the free body diagram. This is where I believe you should always start, is by giving yourself some sort of a small object, a dot or a small square, choosing a direction of motion unless it's decided for you, and then creating a diagram that matches what is causing the motion. So I'm assuming it's moving to the right. It accelerates at a certain rate, which I'll use later. But what I know is that it's being pushed, so there is an applied force. And then I also know that there is friction, which always works against the motion. I'm going to draw my friction arrow a little bit smaller than the applied force because the object is accelerating. So there's less force working against than helping it. The object has a mass, like all objects, so there would be a gravitational force. And then because it's in contact with a surface, there would also be a normal force. And these last two arrows should be drawn the same length because the object doesn't accelerate up or down. It maintains a constant height. It's right on the surface of the table. All right, so what I want you to really try to absorb here is that F equals ma is describing the cause and the effect. The sigma F is the cause, and it comes from the picture. Okay, that's what forces do, is they cause changes in motion. And then the ma is talking about the effect of that, and those are just going to be values that you either have or that you're trying to find. So really use the picture to determine the left-hand side of your equation, and then build an equation and let your algebra take over. So in this case, the arrow that points with the motion, notice that my motion arrow is to the right, my applied force arrow is to the right, so that's going to be my positive force, so I'll write that first. And then I have the frictional force working against the motion, opposite direction, so I would subtract. And that is what must equal the mass times the acceleration. So this statement here describes the cause and the effect on that object. And then I can begin putting in some values here. The applied force is my question mark, so I'm going to leave that as a variable. The force of friction is 8. My mass is in kilograms, that's the 1.6, and my acceleration is 2.5. And when I go through and do my algebra, I find that my applied force is indeed bigger than the frictional force, like I expect, and it is 12 newtons. Okay, so try not to memorize just, oh, it's a box on a horizontal surface, so I'll just take applied force minus friction. Try to really build it so that you can handle any situation you're shown. Again, stop the video if you'd like to copy down the problem. All right, so we have a rocket, and I'm trying to find the acceleration of the rocket. Here's the force that a lot of times people forget. A lot of times people forget that if something has a mass, there is a gravitational force pulling down on it. If you just go too quickly on this problem and you're just trying to find acceleration, you might think, oh, I'll just take the newtons divided by the mass. That's my acceleration. But you're forgetting then is that gravitational force that is working against that upward push. Okay, so the upward push or the applied force, that's the 870 that I'm given here. And there aren't going to be any horizontal forces. There's no mention of, wind or something like that. So this is all entirely vertical. But having this good picture here, now I'm ready to build a description of the cause and the effect. What's causing the motion is that there are 870 newtons pushing up, but there is a gravitational force pushing down. And my gravitational force is going to be calculated by taking m times g. Okay, so that's kind of my standard way of doing it. I probably should have written FP here just to be a little bit more formal, but that's okay, either way. All right, so the cause is on the left, the effect is on the right. Then what I have here is that 870 minus, and now m is 16, and then g, we'll assume we're on Earth here, g is 10 newtons for every kilogram, so I'm going to multiply by 10, and then that would equal my mass of 16 times my acceleration, which is what I'm trying to find. Okay, so I would take 870 and I would subtract 160 and take that result divided by 16. And we got a pretty big acceleration here. I wouldn't want to be on this rocket. Okay, that is more than 4 times the acceleration due to gravity, it turns out. So you would feel very strange indeed at that point. About 4 G's would be your acceleration there. But regardless, here's your acceleration. Notice how, setting up this problem with a free body diagram first helped make sure that I didn't forget about this force and didn't think the problem was too simple. All right, one more example here. And this one involves some additional forces, more than we are usually used to. So this is where this method would really be helpful. Again, stop and record the problem if you'd like to. All right, so 2 friends are pushing on this trunk. Joe pushes to the left with a force of 80 newtons. Since there's 2 applied forces, I'm just going to label the values of forces rather than F sub APP. Hiram pushes with a force to the right with 65 newtons. Okay, so that's what I've got so far. So the box is actually moving to the left. Okay, that kind of makes sense. Okay, motion is to the left, but here's the key, is it's actually decelerating. Okay, doesn't look like it's decelerating based on what I've drawn so far if I don't read carefully here. So it goes on, the problem goes on, and it mentions that there is friction, and that's actually what I'm trying to find here. So friction should be labeled backward to the motion, which in this case would be to the right. All right, so these are my forces that I have so far. Because there is a mass, there is also gravity, gravitational force, and then also the normal force. All right, so here's what we have to work with. Our net force, sigma F, is equal to m times a. Again, this looks very complex, very different from other problems, but if I let the picture dictate how I write the left-hand side of this equation, what causes the motion, I should be okay. I'm going to consider this 80 Newton force to be the positive force because it points in the same direction as the motion. Okay, so these 2 arrows that point in the exact same direction define my positive direction. So 80, and then the 65 works against the motion, and the frictional force also work against motion. So that's everything that's affecting the motion, everything that's causing a change to the motion. And then that would have to equal my mass, which is 9, times my acceleration. Now I got to watch out here. It's decelerating, so I want to make sure that I put in 0.8, but negative 0.8 into my work. All right, so the most important thing is to be able to write this statement. Next part is algebra. We'll go through this on this problem since it's a little bit more, a little messier. But this is the most important statement that shows the cause and the effect of that cause. All right, so we have 15 minus f sub f is equal to, and then 9 times negative 0.8 would be negative 7.2. So maybe I'd subtract 15 from both sides, get negative 22.2, and then multiply by negative 1 or drop the negatives, however you want to think about it. So my frictional force has a magnitude or a value of 22.2 newtons.